but
this is with numerical?
Yeah, this is numerical, and you still see scatter wave outside the field 1 and in region 1, right? So I don't know how to include this as the reference structure. In total field, in numerical, it seems like whether there is an option hidden option to treat some object specifically as a reference structure or not. But it seems like at least as a default setting in numerical, if you put a structure like this and put a total field box around this structure, then numerical treats this bump as a scatter. But in principle, a total field scatter wave should be able to treat this as a reference structure. But I don't know if that is possible in numerical or not. Yeah, so
when you write your own codes, I mean, is it easy to generalize to non-planar stuff?
Yeah.
Okay.
Yeah. So I'll also show some cases where you generate oblique instance. So this is the case without scatter. So again, oblique instance wave is generated specifically inside the region 1. But I'll play this again, and I'll stop actually here. So if you see how this oblique instance wave is generated or appear inside the region 1, it actually the boundary of the oblique instance wave propagates in this direction, right? So what I mean is that oblique instance does not appear from here, but it appears at the same time along this horizontal boundary. That is actually another problem of numerical. I'll discuss some problems of total field scatter wave implementation in numerical. So problems of in numerical. So there's no way to assign objects in TF region as reference structure. Or there's some option hidden, I don't know. And an oblique instance is actually implemented using block boundary condition. So this is not truly plane wave, but contains a range of angles. So what I mean by that is if the oblique instance is implemented by block boundary condition, you have this kind of field pattern. But true oblique instance it looks something like this. So this part propagates this direction, and this part propagates in this direction. So and there is difference, and this one has a range of angles, as I discussed last time. But this one is just plane wave, and you can still generate this kind of true plane wave by following the argument that I showed earlier in the first part of the class. So you can just find JE and JM around the boundary that satisfies any that creates any wave strictly inside the region 1. So in principle, total field scalar wave is actually a method to create this kind of true oblique instance, and that is very well discussed in literature. But for some reason, in numerical, it is not implemented this way. So that's the end of the discussion of the total field scalar wave. And as a last topic, I'll briefly discuss the difference between different numerical methods. So there are two categories of distinction. So first, distinction by discretization method. So you have finite difference and you have finite element. By the way, these are not the only two ways to discretize the space, but they are most common discretization methods. And the mesh style. The finite difference has rectangular mesh, which is something like this, and the finite element has triangular mesh, which is like this, and so and for modeling the curved surface, finite difference is easy. Difficult. but finite element is easy. You can easily see why it is easy and difficult because of the mesh style. And parallelization of the solver. Finite difference is very simple. You can just divide, for example, this grid into 4 regions and assign each grid region to different structure and different CPUs. But for finite element, it is involved because when you have the triangular mesh, it is difficult to find the boundary where you have exactly even numbers of mesh points. So you have to, and there are many ways to draw this boundary between CPUs. So to make the good balance between CPUs, it is difficult. And there's also a distinction by the type of Maxwell's equations it solves. So distinction by type of there's a time domain Maxwell's equations. Which is curl of E is minus dt, E, and curl of H is dt, E plus J. And there's frequency domain Maxwell's equation, which is curl of E is minus I omega mu 0 H, and curl of H is I omega epsilon E plus J. So the frequency domain Maxwell's equation is single frequency Maxwell's equation basically. So the algorithm, so implementing these two solvers, the time domain solver is easy. So you just need to evaluate update equations continuously. And for frequency domain equation, it is involved. So you basically need to solve this kind of linear system. So this is typically involves lots of linear algebra. So the implementation is more difficult for frequency domain. And parallelization it is very efficient for time domain, but it is inefficient in the frequency domain. The reason is that there's not a very good parallelized numerical solver for this linear system. There are many techniques, but not as efficient as a time domain solver. And modeling dispersive media. It is inaccurate in time domain because you need to fit epsilon of omega with the analytic function, as I discussed earlier in different classes. But it is exact in frequency domain because you just need to use epsilon of omega for given omega you use in the equation. And for spectral response, calculation, it is just one shot calculation. You can just use a Gaussian pulse, which contains many frequency components, but you need to do frequency by frequency in frequency domain solver. But for steady state calculation, time domain takes long. So in the time domain, to get the steady state solution, you have to wait until all the transient states die out. But in the frequency domain, it is direct. And lastly, for nonlinear optics, you can do nonlinear optics in time domain solver, but not in frequency domain solver, because you cannot handle multiple omegas in frequency domain solver. You just need to, you should fix frequency omega in frequency domain solver. But nonlinear optics usually involves some frequency conversion, things like that. So you cannot do nonlinear optics in frequency domain solver. So using these two categories of distinction, you can probably map different solvers. So discretization method. There are two: finite difference and finite element. And there are Nelson's equation. Time domain and frequency domain. And this is FDTD. So, numerical. And this is finite element time domain. And this is FDTD. And this is finite element frequency domain method. But this is also known as finite element method simply. So this is console. And this is actually area of active research. It's not mature. And this is for FDTD there are many free software. There are not many public free software, but implementation easy. So many groups at Stanford has their own FDTD solver. So FDTD is good for spectral response, nonlinear optics. And FEM is good for precision modeling. Of curved surface and dispersive. I'll just discuss the advantages of these two because there are numerical and console are two of the most popular commercial software. So, are there any questions? This is the last lecture I give in this class, so if there are any questions. Yeah, otherwise I'll go to for finishing up. Yeah, sorry I spent.
No, this was fantastic. I think as much as we like going through the very